thank you for joining us, and let's welcome Gihan.
Thank you, guys. Happy to be here. It's always fun. So as she said, my name is Gihan Gamage. I teach physics and astronomy for the NMSU-Alamogordo campus. Right? That's okay. So today, with the solar eclipse coming up on Monday, I will just give you a brief introduction to boring yet interesting star, our sun. Okay? Why did I say boring? You'll see in a minute. Alrighty. So something that we don't realize is how big this thing actually is. The basic properties of our sun. So if you look at the mass of it, it's roughly about 2 times 10 to the power 30 kilograms. If that doesn't make any much sense, it would take about roughly 332,946 Earth masses to fit into the sun. So roughly 330,000, let's say, average approximation. So that kind of gives you the idea how big this thing actually is. Yes? Yeah. And also how big it is, like size-wise. It's heavy and it's also big. It would take about roughly 110 Earth radii to make up one sun. Yeah, so if the Earth is, let's say, as big as my head, then, sun is as big as my head, Earth would be just a pin drop on the side, just to comparison. Okay? Just like Earth rotates around its own axis, Sun rotates around its own axis too. But since this is such a huge body, the rotation period on the Sun is quite different to what we normally see on Earth. See, on Earth, it doesn't matter if you're on the North Pole or the South Pole or on the equator, it takes roughly 24 hours to complete one rotation around its own axis. But Sun, since it's so big, the rotational periods are different. If you're on the equator, it takes about roughly 26 days. Now we are keeping track of time with respect to stars. If there's science folks, that's what this means, sidereal days. We normally go by solar days, where we keep track of our time with respect to the sun. But for astronomy, we keep track of time with respect to stars, which is a fairly more accurate clock. Okay? So with respect to stars, if you're on the equator of the sun, it'll take about roughly 25 days. If you're on the poles, it's much longer. So this, again, for science folks, I'll try to go between science folks and general audience. For science folks, this is called the differential rotation of the sun. It takes different times depending on where you are at. Okay? Something a little different to what we normally see on Earth. Okay, and the surface temperature, so average surface temperature, meaning the surface of the sun, if you stick a thermometer on it, you'll read about roughly 5,700 Kelvin. In Fahrenheit, that's almost 1,000 degrees. 10,000 degrees. You don't want to be close to that. Okay? And that's just the surface. Later on, I'll tell you, depending on whether you go into the sun or you go above the sun's surface, the temperature will change. Right? And here's another example of it. If you somehow reach the core of the sun, I'm not the tallest guy in the world. If you reach the core of the sun, some magical from some magical way, you will feel about roughly 15.7 million Kelvin. Okay. Again, if you don't know what Kelvin is, we science folks, we use Kelvin to measure temperatures. Whereas in day-to-day life, we use either Celsius or Fahrenheit. So far, so good? Okay. All right. Now let's look at the basic structure of the sun. Okay. And we will go through most of these terms later on. Now I'm just giving you the, introduction of what we're going to discuss. We're going to look at what's happening inside the sun, so the internal structure. And then we'll look at what's happening on the surface of the sun and some nice solar activities such as sunspots and prominences. Good? Okay. So let's start with inside the sun. Sun has a giant energy generator, which is we assume to be in the center. Now these are what I call scientific speculations that we come up, theories that we come up with depending on what we observe. No one has cut open the sun in half and actually looked inside this. Okay? That would be impossible. So given the structure of it, we believe there should be a core where the energy gets generated. Okay? That energy then get transferred to the surface, which we see when we look at the sun. Now the energy transportation happen during in simple terms, it happens using two methods. The first period, we call it the radiative zone, where heat get transferred through radiation. Now, if this is another fancy word for you, there are three ways that heat normally get transferred. One is through convection, like if you're boiling water, you look into the pot, you see bubbles coming up. That's called convection. Then there's also conduction. If you take a metal rod and put it up against a fire, if you're making s'mores in the summer, you normally have a handle that's, or hopefully, that's made out of wood or, well, not metal. Because metal takes heat from one end and runs with it to the other end. So you're going to burn your hand if you don't have some sort of insulation. Right? And the other way is radiation, where heat just travels through some sort of a medium. Right? So first part of the energy transportation is through radiation. So we call this radiative zone. Then, after it travels a certain distance, we hit what we call the convective zone, where it acts like a bubbling pot of water. The heat, the particles that's in this border latch onto heat that's coming from the radiative zone. Then this travels up, cools down once it hits the surface, then goes back down. Just like a boiling pot of water. Does that make sense? Yep. So the biggest problem for a longest time is what powers this core? Like, how do we get energy? And also something that you have to understand is sun is roughly 4.6 billion years old. Billion years old. What powers something to be this old, and what can keep this going? And we know with our theories it will last another 4 billion years for the future. So what would keep this going? So this was one of the bigger questions. First we tried with what we know. We tried with fossil fuel. Sun wouldn't last more than 20,000 years, given its size and the shape. Then we tried what we call gravitational contractions, where things collapse on itself and that creates energy. That wouldn't do it either. Then we came up with this theory, nuclear fusion, where two hydrogen atoms combine together and make helium, right? Forget all the fancy symbols that you see here. Important part is hydrogen atoms combine together and create helium. And as a byproduct of this produces energy. So in case you don't know, gamma ray is high energy light, quote unquote light. It's high energy electromagnetic radiation. And this process will have enough to power the sun for the 4.5 or 6 billion years that it lived so far and in the near future to come. The problem is, how do we prove this? How do we know that this is what's actually happening? Right? We got lucky. This process also emits something called neutrinos. In case you're a little bit sciencey, if you split open an atom, we know there's electrons, protons, and neutrons, and also that's what you're told in high school at least, and say that's the basic structure. But then you go into college, they say no, that's a lie. There are 12 fundamental building blocks. That is what everyone is made out of. Hence the word 12 fundamental building blocks. Okay, every one of us, everything in this room can be split into those 12 particles. Right? Neutrinos are one of those. They are very interesting. They're less heavy. They don't interact with other particles too much. They travel through space with less problems, less interactions with the rest, because they're neutral. Okay? But we never had a method to find this. So if we come up with an experiment to find neutrinos, then we can prove, okay, the energy production in the sun is actually this PP chain, or the proton-proton cycle, or hydrogen fusion. Right? So we did. I think, if I'm not mistaken on my history, Japan took the initiative. They came up with what we call the super chemicant experiments, and little later, Canada created their own experiment called the Snow Lab. It's in a place called Sudbury. So SNOW means Sudbury Neutrino Observatory. There's no W. So this is what they did. They took a giant mine that's not usable anymore. They put this big tank in there. So this is an actual picture. So this is what it would look like. They put this big tank in there, and on this metal frame, they attach a whole bunch of cameras. So these things, tiny things that you see, these are cameras. Okay, and these cameras are programmed to look for something very specific. Right? I'll tell you that in a minute. And this tank is filled with what we call heavy water. So the normal water that you drink, it's H2O, 2 hydrogen atoms and 1 oxygen atom combined. Heavy water has something called deuterium. It's a variation of hydrogen that has an extra proton in it. Now, if that all just skip your head, that's okay. Just remember the word heavy water. Okay? There's a funny story going into the building of this. People protested. Why are we putting heavy water underground? So the scientists actually had to drink a glass of heavy water to show people that it's not harmful. Well, it will be harmful if you drink it too much. But, once in a while, a little glass won't kill you. Okay? So they put heavy water in this thing, and the reason for it is once neutrinos hit that heavy water, it does something interesting. It creates a light cone. So we're all familiar with sonic booms, right? And we know why it happens. Those jets travel faster than speed of sound, which creates a boom. Okay? If you make something go faster than the speed of light, it will create a light boom. Okay? For that to happen, you need to change the medium. So this neutrinos, they're coming through normal space, then they enter this water tank. Remember what I said, neutrinos don't interact with much, so they can penetrate through Earth's crust like it's nothing. That's why we put this thing underground. So minimum disturbances, only neutrinos, chances are only neutrinos will make through the crust and hit this tank. Okay? So when they hit that heavy water, it actually get rid of one of the electrons, and since it has too much energy, this is the story in a nutshell, okay? And make that electron travel faster than speed of light for a split second. This is called the Cherenkov effect, or Cherenkov light, named after the Russian scientist who came up with this idea. And those cameras, these cameras, they are programmed to look for that light. Does that make sense? Right? And we confirmed with this, hey, yes, it does actually happen. So proton-proton cycle is the best explanation we have with evidence to say this is how the sun produces energy. In 2016, Professor Arthur MacDonald won the Nobel Prize for this. He is the founder of the SNO, the Sudbury Neutrino Observatory. The reason why he won the Nobel Prize over Japan is Japan had their instruments calibrated just to look for one type of neutrinos. He made his instruments to look for all 3 kinds of neutrinos. Think about it as ice cream flavors. They come in chocolate, strawberry, and vanilla. We thought because of the energy production of the sun, we will only see chocolate. And they set everything up, looking for chocolate. They only found 1/3 of what you're supposed to find. So we thought, our theory might be wrong. Until this experiment came along, where they had calibrated things for detect all 3. When you did that, it worked. Yes, sun only produced chocolate, but neutrinos does this weird thing where in between they change flavors. You go to the ice cream truck, you get a chocolate, but by the time you get your brother or sister, now it's a vanilla. Okay? That's exactly what happened. Anyways, it's an interesting story, and he won the Nobel Prize for it. So this is fairly recent. Okay, now let's continue with our journey on looking at the surface of the sun. Okay, so normally if you look at the sun, it would look something like this. Yeah, well, not with your average telescope, but maybe with a research grade telescope, it'll look something like this. kind of, every time I show this picture to my students, they get kind of icky. They're like, that's disgusting. But that's actually what it is. It's constantly boiling. You look at it through your own telescope or during a solar glass, maybe, if you try hard enough, you'll see a nice smooth surface, but it's actually not. This bubbling happens because of that last zone, convection, heat constantly coming up, then going down. Okay. If you really pay enough, let's look at the zoom in picture. Do you see that there's a color difference here? There's some dark spots, there's bright spots. The dark spots represent somewhat cooler temperatures compared to the brighter ones are being the hotter temperatures. Okay. So this is what it actually looks like. It's a bubbling pot of water. You can actually look for animations of this. That will really gross you out because it looks like a bunch of worms just running around. I'm not joking. Okay? So we call this structure that we see the granular looking structure, or these are called granulomas actually. Okay? So this is what it looks like. You zoom in, that's what it actually looks like. And people have dedicated their life, they're constantly monitoring these granular activities to see what's going on. Because if this thing decides to do something extremely weird, well, bye life. Right. And sun is, it's not a special star. It's a boring old star. If you're familiar with astronomy, it's called a main sequence star, where it's burning hydrogen into helium to sustain its life. Okay, which is what sun is doing. Normally it's boring, but it has enough to keep us, on our toes, keep us guessing. And then, if you look at the sun using an ultraviolet camera, you don't see, sorry, I forgot to mention a word. You don't see this photosphere. The surface of the sun that we see, we call it the photosphere, right? But if you look at the sun through an ultraviolet camera, it looks a little different. This layer that we see, we call it the chromosphere. Now here's something that we normally don't think about. The light that we see relates to the temperature of the object. This is why if you point an IR camera onto any living being, you see some heat. Agree? That heat is a type of light. It's a type of radiation. Okay? Cooler objects, they tend to be at IR, maybe a little bit of visible, radio. Hotter ones tend to be at high energy wavelengths such as ultraviolet, gamma, and X-ray. Okay? So the fact that I can look at the sun and see ultraviolet emission from it tells me, oh, there's a surface on the sun that's actually emits ultraviolet, that's hot. Sort of makes sense? Yeah? So this layer is actually above the photosphere, and for some reason that I'm not going to explain until just yet, it's actually warmer than the photosphere. Isn't this strange? Like you have a campfire. Closer you get to the campfire, warmer it gets. Yes? More you walk away from it, cooler it should be. Now I'm saying there's a layer on the sun that's further away from the heat source, but it's warmer. This is counterintuitive. This is not something we think about. Okay? But that's exactly what happens. You think this is weird, wait until I show you the next layer, solar corona. It's even warmer than that. And it's even further away from the photosphere. Yeah? So this is what you're going to see if you go to Dallas on Monday. This is what you're going to see if you look at the sun during the eclipse time. The moon will completely cover the sun. And you will see what we call the solar corona, this white area. It's normally high energy emissions such as X-ray, and you don't see it because the brightness of the photosphere masks it out. But moon now act as an umbrella and cover the sun. So block the light from the photosphere so we can see what's happening on the outskirts. Now this doesn't really mean we only look at the solar corona during solar eclipses. No, we actually have missions that are orbiting the sun who has its own inbuilt umbrella. It masks out the sun and look at what's happening outside of it. Okay? And do you guys see these red thingies? Yeah. These are called Bailey's beads. See, moon has, well, just like Earth, has mountains and valleys. Sometimes when the light, well, here the moon is covering the sun, okay? But when light passes through those uneven surfaces of the moon, we see the last scattered light, as I call it. Like what's the color of the evening sky? Red, right? There's a reason for it. Red has a longer wavelength compared to blue color lights. Longer the wavelength is, longer it takes to get out of your way. Okay? So the valleys in the moon send the rest, we can't see the rest of the colors, but it let red comes through. Okay? So these are called Bailey's beads. So the reason, well, for the longest time we couldn't figure out the reason why the solar corona and the chromosphere is warmer than the photosphere, until we started looking at some of the activities that happen on the sun. How much time do I have?
I would say 50 more minutes.
50 more minutes? Oh, okay. Nice. Okay.
Take it, Tom.
Let's look at, before we answer that question, let's look at some of the activities that we see of the sun, because these are kind of all related to one another. Now, one of the most famous activities, that happen on the sun that everybody knows of is sunspots. Yes? I'm not talking about the observatory, okay? I'm talking about the actual sunspots. So when you look at the sun sometimes, you see these dark spots. Right now, we are at a solar minimum, so I think a couple of weeks ago, there was a big sunspot that was actually bigger than the United States, actually 3 times or 4 times more than the whole Earth, actually. That was on the sun, and these are even probably bigger than the size of the Earth. Okay? These are not actually just dark spots. They are comparatively cooler in temperature to the rest of the surface of the sun. For example, let's say the surface is at 5800 Kelvin, the sunspot might be at 4800 Kelvin. Still warm, but compared to its surface, compared to its surroundings, it's cooler. So then they tend to appear darker in color. Okay? So we study these sunspots basically mainly for one thing, to look at the magnetic activities on the sun. Now, let's track back a little bit. You all agree that Earth has a magnetic field? Yes, if not, yes, Earth has a magnetic field. The reason for it is Earth has a liquid core. When liquid ionized particles floating around, it creates a magnetic field. One of the basic principles of physics. Sun is full of those charged particles that's glowing around. Sun is mostly plasma. Again, this is another lie that you were told in high school. You were told there are 3 states of matter. There's gases, there's solids, there's liquids. Guess what? There's a 4th state that we don't normally study much. It's called plasma. Sun is full of plasma material, so it's a state between liquids and gas. It's ionized, it can float around, it can move around. Anytime a charged particle is moving around, it creates a magnetic field. Given this being 110 times bigger than the size of the Earth and mostly full of liquids, think about the size of the magnetic field coming out of this guy. Yeah? If you don't believe me when I say charged particles create a magnetic field, go home, take a nail, wrap a wire around it, hook it up to a battery. You get yourself a temporary magnet. Okay? Because the fact that you wrap the wire around the nail, now your current is constantly changing direction. Your electrons are constantly changing directions. So that creates a magnetic field. This is how in junkyards, they have that big circle that's running around, and then all of a sudden it can latch onto a whole bunch of metal, then go toss it off. Have you ever wondered how come this thing is moving around without latching onto all the cars that's there? It's because there's some guy with a switch. He switched the magnet on, he can switch it off. Okay? These are called electromagnets. Anyways, so Sun's magnetic field, Sun has a gigantic magnetic field, 1, and 2, because of the rotational speeds of the Sun. Remember, in the very first slide I mentioned, because of the size of this thing, if you're on the equator of the Sun, it takes about roughly 26 days to complete one circle around its own axis. If you're on the poles, it takes much longer. Now, because of this difference in rotational period, the magnetic field lines on the sun breaks. They get twisted and then they break. When the magnetic field lines break, the matter actually, the plasmaric matter that's on the surface, that's on the sun, tend to come out. So think about it. You have a hot surface, now you just put your hand in and you just grab something out. Yeah? So temporarily that area is now cooler. Make sense? Okay. So that's how, in a nutshell, sunspots get created. Now you gotta understand these guys. These are things that people spend their lifetime doing research. Okay? And I'm trying to explain all this in our lecture. Okay. So the next activity kind of falls in line with the whole idea of sunspot is solar prominences. Okay? When those magnetic field lines break, that matter get ejected, but they still have a charge. Because of this, they get anchored back to the sun. You see that? Look at the size of the Earth compared to the solar prominence. If we happen to be in this, we're toast. Okay? And sometimes when you look at the sun through even a decent enough telescope, you can see the solar prominences. The problem is you have to be lucky so that the prominences will line up on the edge. Because if it's lined up on the surface, the prominence is coming at you. It's really hard to figure out whether it's the surface or it's coming at you. But if it's on the edge, then you can see it quite decently. Right? So these are the same material that's in the sun. Magnetic field lines break, it get ejected, but they're charged, so they get anchored back to the sun. Right? This creates solar prominences. Sometimes they have too much energy. They don't get anchored back. They get ejected. Okay? This creates what we call coronal mass ejections, or CMEs for short. Now, not to scare you, if one of these things hit, let's say there's a CME that happened on the sun and we are on the dead center of it. Well, bye-bye life. We're going to knock out all the satellites that's in orbit. We're going to lose all our electricity. Well, we might even, because of everything crashing on, we might all die. Okay? But here's the good part to it. Sun is this big and we are just a pinhead. Right? So chances of these things lining up perfectly, it's literally astronomical. Okay? So don't get too scared. Don't go home and build a bunk. Okay, so when these material get ejected, after about a couple of days, 2 to 4 days, because they're gonna travel a little less. So let me trace back a little bit more. Have you ever heard of this? That we see the sun as it was 8 minutes ago. Yeah, because light travels at a finite speed. Okay, given the distance between the Earth and the sun, light takes about 8 minutes to reach us. Right? That's light without any mass, without any interactions, nothing. But these guys, yes, they are high energetic, but they still have a mass. So they travel a little less in a smaller speed than speed of light. So they take about, instead of 8 minutes, they take about 2 to 4 days, depending on how much energy they had. Energy the explosion had. Then by the time it reached the Earth, then the Earth's magnetic field come into play. Now this is one of the problems we have with trying to find a living on Mars, because Mars doesn't have a magnetic field like the Earth does. So if something like this happen, well, we're not going to survive at all. On Earth, we might survive maybe. Okay? So here's a nice animation of, oh, no, wait a minute, that's a different thing. I'll show you something in a minute. So the these particles, they come and hit Earth's magnetic field, and then Earth's magnetic field lines, we call it a magnetic field line breaking. They break, they connect on the other side. Then once they connect, the material that comes through these ionized particles that comes through the CME get funneled through those magnetic field lines, which creates auroras on Earth north poles and on the poles. Okay, I'll show you an animation in a minute. Sometimes when these ejections happen, it's not actually matter that comes out, it's just radiation, it's just heat. Okay, these are called solar flares. You thought, if you think CMEs are bad, These guys are worst. These are much more high energetic than CMEs, right? These things hit Earth, then the same phenomena happens. Okay, so the difference between the two is the CMEs, these are mostly matter, these are mostly radiation, right? Either one of these, now here's a nice animation I was telling you about. See the magnetic field lines break, things get scattered. Now here, Earth's magnetic field coming into play, they combine on the other side, and as they do, you see the matter funneling through and creating these nice auroras that we see on Earth, right? Sometimes, depending on how energetic the event is, we might be able to see it, because normally you gotta go into northern latitudes to see them, but if it's very energetic, I think there have been incidences in history where auroras lit up the sky and you could see it in southern latitudes like we are. Okay. This is my friend / student Vincent. He is currently doing his PhD in University of Arizona Fairbanks, and this is what he does for a living. He goes around and takes pictures of auroras. I think that's one of the coolest jobs that you can find. Well, if you like the cold. If you don't like the cold, then forget about it. Recently, I saw him going on a husky ride to one of those very remote places in the northern pole to take aurora pictures. That guy's crazy. Okay, now the big topic these days is the solar eclipse that's happening on Monday. Yes? In case you don't have how this happened, in case you don't know how this happened, here's a little brief summary. So, we got to think about a little bit of a relative motion here. Earth spins around its own axis, and we have a moon that rotates around us. Yes? So, we think everything is on a pancake, on a flat surface like this, but it's actually not. I mean, even if you take a pancake, it has a thickness. Yes? It's flat, but it still has a thickness. So because of this, there comes some time where all of these line up right on the dead center of the pancake, or let's say the top layer of the pancake. Okay? When that happens, moon would be in between the Earth and the Sun. Okay? Which will cast a shadow on Earth's surface. Does that make sense? Now, the reason why this doesn't happen, let's say, every 30 days is because, well, they're not going to line up all the time. Okay? Sometimes it's going to be like this. Sometimes it's going to be like this. When it happens to line up on the same plane, you get a solar eclipse. Okay? And if you happen to be in this center dark dot, you're going to see the whole sun disappearing. Okay? So this is called the path of totality. So that's what I meant. If you go to Dallas, which I believe is the closest to us, you will see this. The whole sun will disappear. The moon is big enough to cover the whole sun. Okay? And you think, oh, that's the end of it. No. There are different kinds of solar eclipses. Remember, there was one that happened, what was it, October last year? Yeah? And then there's another one happening in April. There are two different kinds. Okay? So the one that happened in October last year, it's called an annular solar eclipse. Now, yes, the moon rotates around the Earth, but it's not actually a circular orbit like we normally draw. It's more like an egg. It's an elliptical orbit. Okay? Now, because of this, there comes time where the distance between the Earth and the moon is different. Okay, let's go back to my previous picture. So when they line up, there comes a time moon is this close to Earth, and there comes a time moon is, let's say, this close to Earth, a little bit further away. Okay, so now you got to think about in a relative motion, like in a relative way. If I make a fist and then try to cover it with my little remote, I might be able to, I might not be able to. Okay? But if I push this remote further away, there comes a point I can actually cover it. Does that make sense? Okay? So this is the difference between an annular and a total eclipse. In an annular eclipse, moon is closer to Earth, so it can cover the sun completely. So it leaves this nice bright ring around it. In a total eclipse, moon is further away from the Earth, then it can cover the sun completely. Yes? Okay. And there are some times it can cover just a little bit of it. Sorry. These are called partial eclipses. Now, partial eclipses can happen on its own, and also if you happen to be out of the path of totality, you would see a partial eclipse. For example, even the one that happened in October and the one that's going to happen on Monday, it is an annual eclipse and a total solar eclipse, but we are not in the path of totality. So for us, it's going to be a partial solar eclipse. Does that make sense? Right? So this is a total, this is an annular, and this one is a partial. Yeah. Now my students last year, they went up to Roswell. So Cheryl, she went up to Roswell to look at the annular solar eclipse, and this is what she saw. This is almost at the dead center. As you can see, the ring up here is a little thinner compared to down here. If she had taken this picture, like maybe 10 seconds later, it would be in the dead center. Right? And also, this is my friend, Dean Smith. He went to see the solar eclipse that happened in 2017. We were in Idaho, and this is during the totality. If you get a chance to go, please go. It's a different experience. Things go dark for like about a good minute or so. Things kind of get freaky. Things get cold. You're gonna start seeing like two shadows. So it's an interesting experience. And in case you didn't get a chance to look at it, here's the path of totality. Like I said, Dallas will be the closest to us, or Arkansas, wherever you can go. Enjoy. If not, be here. We'll have something set up in the museum for you to look at the partial eclipse or partial version of the total solar eclipse that's going to happen. Yeah, and more importantly, don't forget your solar glasses. Okay? I saw a meme that came out of I think it's Maine Transportation Department that said, "Don't drive with your solar glasses on." Right, and thank you.